Gracias. Buenos días, jóvenes. Bienvenidos a Ciudad Altamira. Bienvenidos a esta quinta edición del Encuentro de Materiales y Dispositivos Altamira 2025. El día de hoy vamos a tener ahorita el primer bloque de presentaciones de ahorita a las 11:30 de la mañana. Vamos a empezar con la plática impartida por el doctor Pramod Kumar Singh. El doctor Pramod Kumar Singh es el director del Departamento de Física e Ingeniería Ambiental de la Universidad de Sharda en la ciudad de Greater Noida, en la India, que es una universidad privada. Estudió su doctorado en la Universidad Hindú de Banaras, en Varanasi, en la India. Se dedica a la docencia, la investigación, la administración y la consultoría por los últimos 25 años. Ha publicado más de 377 artículos hasta mayo de 2025. En revistas internacionales, ha sido autor de 7 libros o capítulos de libro. Está entre el 2% de los científicos más importantes en el mundo, según el ranking de la Universidad de Stanford. Ha visitado Surcorea, la India y Turquía, entre otros lugares, como profesor invitado, como postdoctorado. Es parte del comité editorial de ocho revistas internacionales y ha presentado una serie de artículos y conferencias en diferentes lugares del mundo. Sus áreas de investigación son electrolitos poliméricos, materiales para dispositivos de energía, manejo de residuos, y es director del Centro de Excelencia en Energías Renovables y Celdas Solares en la Universidad de Sharda. Dr. Pramod Kumar Singh, we are very pleased to have you here in our conference. The room is yours. You have 25 minutes, and after some questions from the public. Thank you very much. Welcome to our event. Doctor?
Yeah, I think my voice is clear.
Yes, it's clear. We can hear you.
Okay, so thank Philips. At least in Indian time, I want to say good night. Not I can say good morning because it's Indian night time. And right now the time is 9:30 p.m. So you can say we as a Indian are 12 hours ahead in comparison to Mexico. So from my side, from Indian side, I must welcome all of my graduate student, as Philip is my close friend, and he already informed me this presentation is not like a, you can say, conference presentation. It is a presentation, something about science, which is correlated with, you can say, graduate student. So I can, you can say, modify my own slides according to graduate student, not as a conference participants where too many international participants or researchers is sitting. So this talk is totally dedicated to my friend Philip, and I think he has already visited my institute in India, I think long ago, and we especially invite all of his students, maybe you can say professor, student, to visit India, because India is a very versatile country, and I am leaving the current position of my own institute. I think Philip know better than me. I am residing in capital place of India. So center part of India, which is known as, my capital of India is known as Delhi. So my university is located around area. So I have divided my whole talk into two parts. In one part, little bit glimpse I am giving you to India. What is India? What is the specific things about India? And then I am coming to my own part, my research area or my teaching area or whatever, the area where I want to maybe interconnect with my student nationally and internationally. And then finally, I am going to draw in front of you conclusion. And I am, as a good teacher, maybe I am also going to maintain time limit, because time limit which you provide for me is 25 minutes. So something about India, Before going to India, I think I am give you a little bit about the things which is related to my own work. So here Sharda University is located, as I have already told you. It is in central part of India, nearby capital, and capital of India is known as Delhi. So my university is located nearby capital, and I am heading physics and environmental science department. Both department, you can say, very much correlated with recent topic of conference. So many things related with energy, environment, and material science. So I am heading these two departments here in Sharda University, and I with my team member, you can see, these are my colleagues. These are my, you can say, departmental colleagues who is maintaining the whole laboratory environment. So none other than some of my colleagues which is sitting here, and the title where I want to give little bit glimpse to, you can say, my student, graduate student, and the title of talk is Low Viscosity Ionic Liquid Doped Polymer Electrolyte for Energy Application. So this is, you can say, in the part of research. As I have already told you in starting slides, little bit glimpse I am giving you about India, and then I am coming to my own research topic, which I think I have. So coming to India, I think no better than a judge, you can say, is Philip, because he have already come to India. So as an Indian, in India, we have 26 states. States means little part of, you can say. So we are divided into 26 specialized states. And capital is New Delhi, where I am located. So you can say, if we can divide by corner, you can say East India, West India, North India, and South India. So little bit things about Indian, you can say, hidden part I am going to tell. So as a food culture, we are totally different. If you come to India, north side part of India, you can get maybe North Indian foods, which I shown here. It's like chapati, curry, and very famous things. If you go to west part, you can maybe get West Indian dishes or something. If you come to, you can say, east with north side, you can take totally different foods. And south side, if you go, you can say South Indian food. So in food, we are totally different. I cannot say that we are totally different. We love each part, east, west, north, south. But whenever you go to another part, you can maybe give a difference. So I invite all of you. If you want to take, you can say fish, curry, and chicken type, you must visit to North Indian part. And if you want to take some rice, chapati, and other kind of thing, you must visit to South India part. So we are very versatile, you can say, class of foods. Along with, you can see, my own culture for India. So east side, west side, north side, seven side. We are also wearing different type of clothes. So culture, humanity, you can say, our religion, our food, everything is different. And particularly for us, like Indian, I can say that we have different languages. If you don't know, you must be understand about Indian culture, Indian diversity. We have different language. We have different writing script. If I go to south part of own India, I cannot even try to understand. I do not write their own language. So for me, in India, if we want to move like, or if you want to enjoy like a, you can say, Western culture or any other country, maybe we can put it upon in your own, you can say, south side. So India is very versatile in food. You can say your wearing clothes, our culture, our, you can say, religions, too many religions, but we are sitting together. And whenever we meet internationally, I am talking about a story, whenever you can meet with any Indian, when we are going abroad, we say we are Indian. But when it comes in our own state, we are belonging to north side, south side, east side, west side. but we are joined together and we have a one common language, you can say Hindi, which is very popular, but not in too much states. So common language is English. That's why we are suffering, and we are not suffering any language barrier and other things. So this is something about India, and my university is, as I have already told you, it's located in central part of that. So this one is something about India. Anytime you are most welcome to come and visit with Indian things. Now I am coming to my own topic, you can say, the area where I am working. I have already told you that the area of my choose is, you can say, is related with science. First one thing, low viscosity ionic. So viscosity, this word, is related with physics. If physics people sitting here, maybe might say anywhere, viscosity is a physical property which is related with physics. Ionic liquids is known as eutectic salts. And this eutectic salts is related with chemistry. And if you join together, you can develop any new material. Then you can apply this material in any device. So something in my talk, you can give little bit about, you can say physics, chemistry, join together, there is application part. So something related to device part, I am going to tell in front of all audience because it's an undergraduate student. So I am not going to tell you different things related to, you can say specific about physics, chemistry or any other part. So my talk is totally dedicated to material and device. Materials, I am talking about some own materials, my own PhD work, which is related with polymer electrolyte, and device, which I am going to tell you little bit things. It's related with supercapacitor and solar cell. So I think as a graduate student, many graduate students are sitting here. Might you have seen solar cell on your top floor, or when you are going to buy road, there is solar module. And nowadays, each country is facing too many problems with, you can say, pollution, carbon dioxide emission, CO2 emission, and other things. So, solar cell is already provided you a abundant solution, a novel solution to reduce these pollutions. Solar cell is everywhere. I am talking about the solar cell, which is not solid state solar cell, which you have seen in, you can say, road or maybe your top floor. I am talking about photoelectrochemical solar cell. Something related to another one device which I am going to talk or want to talk something related things. It's known as supercapacitor. Supercapacitor, you can divide into two parts. One is super, another one is capacitor. So capacitor, I don't know how many of you have, but whenever we are too much, you can say, in baby stage or younger side, that time we heard in good, you can say, radio, where we have not that time not too much popular about, you can say, our cell phone and other things. So we have a radio machine. And inside that radio, whenever we are going to switch on, there are too many condenser. That one is known as condenser that time. So condenser is a device which can collect charge. Now, new terminology came, and that one is known as supercapacitor. Another one device which have too much, you can say, storage ability. That's why its name is super. So something I am going to talk about supercapacitor, which is popular in market. Now I have already shown you one figure. This popular supercapacitor is now available in, you can say, market. You can purchase it by giving some money. And now the solar cell which I am talking, it's related with photoelectrochemical solar cell. So I have already told about something about India. Now I am coming to particularly about my laboratory. So in my own laboratory, we have graduate student, we have master student, and you can say we have PhD student. So whole soul laboratory, you can say, where I am heading. I am giving you one configuration, like you can say family head. This, you can say, laboratory is known as Center of Excellence in solar cell and renewable energy. So short name is COESCRE. And you can say I am heading this laboratory. So head is myself. You can say younger brother, or maybe you can say guardian, grandpa, something like that one. And this laboratory is totally governed by a carbon cycle. So member, it's governed by members. Member is none other than, you can say, my own faculty member. So colleagues within Sharda boundary is known as members. And these members are totally governed by, you can say, they are going to capture our core team. What is core team? Core team is my PhD student. PhD student within Sharda University. So PhD student is governed by these members. And now these, you can say, core team member, my PhD student, some of my PhD student is also listening this talk, you can say. So if I am not correcting judge, they are going to tell me tomorrow where I am going to be like now, are going to be flaws. And these core team is going to govern my students. These students are my undergraduate student, postgraduate student, and graduate student. So whole carbon cycle, you can say this one is my laboratory structure, where we have governed, you can say, undergraduate student, graduate student, along with PhD student. And I am heading this center. In this center, we are focused about material synthesis. Then characterization means the machine which can give you that whether your material is good or bad or something like that one. And if we feel that our developed material is too much good, then we are going to apply it in devices. Some devices which is popular in market, and two popular devices where I am working, particularly with, you can say, my friend Philip Noida. Two devices known as photoelectrochemical solar cell and supercapacitor. I also want to work, I don't know when and how, but I also want to work something about, you can say, actuators, batteries, sensors, and many more devices. But right now, my laboratory is only focused around solar cell and supercapacitor. Now I am coming back to supercapacitor. What is supercapacitor? Supercapacitor, you can understand, it is made by two electrode, and in between that one there is a electrolyte. If you see cross-sectional of these two supercapacitor which is come in market, if you are going to cut it, the structure is looking like that one, where I have already shown in bottom side. There are two electrodes, and in between that one electrodes, there are jelly material, liquid material, or maybe solid material. And that material is known as electrolyte. So you can consider just like two breads, and there is a beach, there in between that one, there is a cheese layer. So if you take a cheese layer in between two breads, that one give you supercapacitor device construction. Same construction you can use in solar cell, photoelectrochemical solar cell. In place of two breads, these two breads maybe you can consider as two electrodes. And this, the middle portion, you can consider is as a electrolyte. So what is difference between supercapacitor and you can say solar cell? As a researcher, I can say in solar cell, we want to use in two electrode conducting materials, semi-conducting materials, particularly to make solar cell, because solar cell is totally governed by semiconducting material. You already read in, you can say, intermediate classes that semiconducting material is a variety of materials which can use in semiconductor industry. So solar cell industry is totally governed by semiconducting material. So you can say there are two braids, and two braids is nothing, I think that there are two current collector, and upon that one there is a layer of, you can say, semiconducting material. Then that sandwich structure is known as solar cell. And if there is a layer of, in place of semiconducting material, there is a layer of porous carbon material. then that device, similar device, is known as supercapacitor. So basic difference about supercapacitor or solar cell is electrode type of material. And electrolyte, we can use a single electrolyte in between that one. Now moving forward to coming something about solar cell. These are the equipments which already you can say in my own laboratory, where you can characterize that your sample is good or bad or something like that. So ionic liquid, since there is a small time, so I cannot say many things about ionic liquid because audience is a student. So whole sole use of either ionic liquid or any material is just to increase conductivity. If in between there is a cheese layer, I have already told you, and that cheese layer is considered as a electrolyte. And if your electrolyte is not good conducting, then you are not able to make device. So whole soul story is related with how I can develop a good polymer electrolyte just sandwiched between two electrodes. So ionic liquid is a very good materials. Maybe chemistry student know it, which you can fill in polymer electrolyte, conductivity going high. So we are using ionic liquids in current, you can say DES system in solar cell, as well as you can say this supercapacitor area, and we found very good results. So these are some useful property of ionic liquid anybody can find in literature. And these are some characterization tools. Characterization tools means the materials when I develop for high conducting, then I am going to test it, whether my material is fit for device or not. So these are the some, you can say, characterization tool, which I cannot say in front of a student. And I can say, if you can see a black dot in between this white portion, then you can say our material is porous. I want a porous material where electrolyte is, you can say, penetrate in between two electrodes, and I can maybe got a good device. So this one is known as, you can say, same picture of our own device, which is known as electrode material. You can say electrode cross-sectional picture is looking like this one. This one is another kind of machine. I think Philip know it. It's known as transmission electron microscopy. And if we are as a researcher, or you can say as a good researcher, if you find this kind of force, we always feel that our material is very good. So these are some old, you can say, story where we can find too many things. And this one is the one method where using which, since there are students sitting in front of me, this is very small method. Maybe you can demonstrate in your own laboratory. And if one time you can say online in lectures or offline lectures, I can tell you how you can develop a polymer electrolyte in laboratory point of view. It's very easy. You can take dopants, you can take your own materials, just dissolve into one solvent, pour into petri dish. Because it's a polymer electrolyte, you can get a very good film. And you can sandwich the film in between two electrodes, and you can measure its conductivity. So this one is the machine using which, that machine is known as electrochemical impedance spectroscopy. And we have found that if you put ionic liquid, your conductivity is going too much high. These another characterization tool, these machines are known as X-ray diffraction pattern. And this machine say that ionic liquid, if you can put, you can get a very good high ionic conductivity by reducing crystallinity, crystalline and semi-crystalline. I can say crystalline means too many particles if joined together in a connecting way, there is no one gap to put impurity. That one is known as crystalline. And if you can find a hole in between these two, that one is known as amorphous portion. So amorphous portion is always good for, you can say, conductivity enhancement, which is shown by these XRD results. And this XRD results, and the another one, you can say, characterization, or last characterization, which I am going to show you, because these are students in front of me. This one instrument is known as differential scanning calorimetry. So try to understand the only language. Language means the heading you can understand. If you read the machine full name, differential scanning calorimetry. So differential is related to difference. Scanning, it's going to scan, and calorimetry is related with temperature. So these results also show that our material is very good. I am going to tell you, you can say abroad, whenever you are coming in any conference or whenever you have chance, you can visit India, we can show you too many things. Now, when this story, this one is maybe probably last slide from my own side, or maybe second last slide. So this one is, you can say, one graph which I always show in front of my students. This graph I carried out when I am doing postdoctoral studies in, you can say, South Korea. So that time I have not measured that. Never I have used that, you can say, solar simulator, the machine which giving you solar cell efficiency. But when I use my same materials in South Korea, that time I got a very low efficiency, but I feel very blessed. Nowadays, using same electrolyte, since I am passing too much years in this area, and now we are getting too much efficiency using, you can say, same polymer electrolyte, still I am not happy, because we have passed too much long time, and we assure that you have capability. As a student, you have capability that till now I am achieving 4%, nearly 4% efficiency in our solar cell, and I expect more than that one from your own side, from my student side. If you know something than us, if you know something better than us, maybe you are the key player which you are, where we can expect that you are in coming time, you are going to show us too much high efficiency. So this one is the efficiency. You can see when I got in South Korea, I am very happy. And now these kind of efficiency, highest efficiency we are getting on our lab in India. Now come to just 1 minute or 2 minutes in another one part, supercapacitor, as I have already told you. This one is very much correlated with new students. You already know about Pepsi, Coca-Cola, and other bottles. So what we do, particularly for our undergraduate student, they have collected these bottles nearby shop, nearby things, and we have processed this, say, you can say, plastic bottle, and made carbon-based material. And this carbon-based material, as I have already told you, it can be used in supercapacitor device. So we have published a very good paper in very good scientific journal, and that journal is known as Nature Scientific Reports, where these students, my own undergraduate student, had developed this carbon material. My PhD student who are listening me, they have developed porous carbon electrode, and jointly with my team member, we are able to, you can say, develop a good supercapacitor. And since it reduces, you can say, pollution, it's a very environmental friendly approach. So we got a good money of in pharma fellowship to my student, and particularly government to give me some project money to further elaborate these things. So these small, you can say, experiment only dedicated to my students who have done a lot, and now I am getting too much good result and too much good money from government side. And now we are able to give you can say, good supercapacitor in laboratory farm, where we are getting nearly 300 farad per gram. Because if you see my old slide, I am going to tell you, the market, the supercapacitor which is available, it's nearly farad per gram. And now we are getting 242, but it is only on laboratory scale. But we believe that if you are going to get this kind of material in coming future, you are maybe develop a product which is much better than company product. So these are the things which I want to show in front of my student. These are, you can say, my team members. Some of members are already joined this one. And these are my collaborators. I can say, I can put Philip photo in front page, because he have already collaborating something with me. He has visit to my laboratory with his own family, and I invite all of you to join my laboratory, maybe online or offline. Nowadays it's easy. you cannot say that you cannot visit Dr. Singh laboratory because it's online. Everything is available online. You send me a request, I can maybe arrange one online visit to all of you just to show our laboratory, and some of my students is going to help always. So these are my friends who using all these friends I have learned a lot, and now the innings here is you. Maybe if you can go visit with them, meet with them, you can gain, maybe you can gain too many things, too many new things from my own side, from my collaborator side, and other things. So these are my some of student, which already they are some my graduate students, some of my students who got BSc degree, bachelor degree in Sharda University. Now they are getting master degree abroad. Some of master students, they are going to get their, you can say, PhD degree. And some of PhD degree holder, now they are getting their postdoctoral study from abroad. So I am lucky enough because as a teacher, I have trained some students who are gaining something from my own side. Now they are spreading all over world, and using that all over world student, I'm enjoying a lot. And thank you, Philip, for giving me this opportunity, because this one is the last one slide. You can say, since our work is related with the environment, so we are also captured in newspapers, media, and other things. And thank you, because you have invited me, and I most welcome if any question from audience side or maybe student side. Thank you very much.
Como marino en la Marina Mercante, fue marino de la Marina Mercante. Trabajó como profesor asistente en MITS en Gwalior. Estuvo en el Boston College of Professional Studies en Gwalior, en el Hindustan College of Science and Technology, en Mathura, que es un colegio del grupo de Sharda, también de las universidades privadas. Ha sido vicerrector asistente de Bienestar de Estudiantes, coordinador de misiones en el Colegio de Ciencia y Tecnología de Hindustan en Mathura. Ha sido revisor en muchas revistas internacionales como Solid Phase Electrochemistry, American Journal of Material Research, etc. Trabaja en electrolitos poliméricos y celdas solares sintetizadas con pintes, usando electrolitos poliméricos, celdas solares sensibilizadas con puntos cuánticos, efectos de la radiación de iones sobre polímeros, electrolitos poliméricos, etc. Actualmente trabaja como profesor y como vicerrector de investigación en la Universidad Oriental en la ciudad de Indore, en la India. Dr. Amit, we are very pleased to have you here. I will let you with these students. They are from the engineering of nanotechnology. So you have 25 minutes plus questions.
Okay, thank you. Thank you. Thanks a lot, Professor Philip. I'm so glad to have an interaction again, and I'm very sorry that I could not visit your campus. I was planning to visit, so welcome to all the students sitting here to tolerate me for next couple of minutes. I don't know how much I can give you, but I will try to give the best. And I suppose Ganeshan is also there, so my wishes to Ganeshan as well is sitting there. I seen that he's asked some question to PK. Good. Although I'm thankful to Professor PK Singh, because he made my presentation quite easy to make you understandable that what actually polymer electrolytes are, or what is the importance of polymer electrolytes, and how the capacitors, supercapacitor, DSSCs, rechargeable batteries, how they actually perform, how they work. My idea is something beyond that presentation, which has been given by the Professor PK Singh. I will focus my presentation deliberately on how the characterization is going on. Like, whenever we are saying that we are conducting, we are preparing the polymer electrolytes, and we are planning to synthesize any energy storage device. In particular, we can say the electrochemical devices, where all these batteries, supercapacitors, rechargeable batteries, solar cells are come into that area. Whenever we are preparing that sort of polymer electrolytes, and we are preparing any material or devices, then we have to characterize them whether this material which we have prepared are up to the mark or not, whether these materials can serve our purpose or not. So when we are making that characterization, impedance spectroscopy is one of the key roles. The key characterization or key experimental setup to find how the materials having the ionic conductivity. So in the today's presentation, I will let you know what is the impedance spectroscopy is, how to use this impedance spectroscopy to calculate, to analyze the conductivity in a polymer thin film, or we can say solid polymer electrolytes. And also, I will let you know some more theoretical models which can be used to understand more deeply about the behavior of ionic conductivity. And in the past couple of months, we have been shifted. We are trying to move ourselves from laboratory to the AI-based system. We are working on some machine learning, AI-based data set and all things. And we are trying to incorporate the idea of machine learning and the DS into the analysis of physics, right? So my introduction is I'm Dr. Amit Saxena. As I'm thankful to Philip that he has given a very brief introduction about me. Currently, I am working the Dean Sciences and Director IQAC at Oriental University, Indore. Although the PK Singh has given a very brief idea about India and all, so I am skipping that part. Directly coming down to the better batteries. I'm saying batteries in particular because already PK sir has discussed about the different types of electrochemical devices. Before going into deeper part of the batteries, let us discuss something about what is the difference between the batteries and supercapacitors, because nowadays the research are going more intense towards supercapacitors. So when I'm comparing with batteries and supercapacitors, so supercapacitors are something where they have very high power density, but at the same time they have very low energy density, and they are being basically on they charge electrostatically, and they are good enough, but they are not providing the good energy. While when we are operating any devices which has been on the energy storage devices or something like your mobile or your batteries, we want good energy density basically. So supercapacitors are not serving that purpose. Still, the research are going on because supercapacitors can show very good charging. Very quick charge can be done in supercapacitors. At the same time, the batteries are one where we have very high energy density, but we have very low power density, and they are being charging slowly, but they have a very long life cycle. They can stay back for more than 48 hours, or now we have some batteries which can stay back for 72 hours. Like that's why you can play a game and all things with your mobile and all things. So, what is the bigger problem when we are discussing with batteries? So, the bigger problem is in the traditional batteries, we have liquid as electrolytes, right? And when we are coming with the liquid, we have so many limitations on that. Like we have the leakage problem, we have the fire problem, and environmental hazard, explosions have been possible. So liquid electrolytes are now abandoned nowadays. Nobody wants highly maintainable batteries. We always think about low maintenance batteries. The solid batteries are the alternate of that type of traditional battery, right? So what is the advantage of solid state batteries are they're flexible enough, and they are non-toxic. They are not leakage. It's a leakage proof. And when we are coming with the solid state batteries, there's very less chances of getting explosion. Although there may be some chances when we don't have a proper composition of the electrolytes and the two electrodes which have been used to sandwich the electrolyte, there may be some problem. But in general, solid state batteries have the protection that they will not be exploding in comparison to the liquid counterpart of the liquid. So when we say that solid electrolytes are the good alternate or the good solution to liquid part, then the question comes then how we can prepare. So before presenting this slide, I am thankful to the AI and ChatGPT because they can do so many things for us. So this particular diagram is been prepared by uh, one of the tool which we know as notebook LM, right? So I think most of you are aware of these type of AI tools. As I already mentioned that nowadays we are moving toward more AI-based system. We have so many software we have developed in our own laboratory, which has been used by Python and R, right? So some of my students are working on Python and they are developing some tools on that. So I'm also trying to get familiar with the AI tools. Yeah, so I'm thankful to the AI tools, and someone can see that what is the best method of the solution cast method to prepare a solid self-standing polymer electrolyte films. One first step is to dissolve the host polymer in a solvent, then keep on adding what plasticizers, what type of disperside or what sort of salt you want to make it sterile for a long time. In general, we make sterile for more than 24 hours, and then we pour it onto the polypropylene petri dish, and we keep allowing the liquid part to evaporate so that we can get the self-standing thin flexible films. And further, for getting the more insight on that film, we make the characterization. As I already mentioned, that I'm not going into the structural or the optical properties. I am more focused on the electrical properties. That's how the conductivity is going on, what is the ionic conductivity, and what is the electronic conductivity. So for that, we are using the impedance spectroscopy. So the conductivity is a big puzzle. And why it is a puzzle? That's the reason. Most of the polymers which we have are either crystalline or partially crystalline. You can see when something is crystalline, then whatever ion we have, which has been because of the salt which we have dispersed, they all been trapped into the crystalline phases, and the ions cannot move through the two sides of the electrolyte. So what we are trying to make is we are trying to reduce the crystallinity, and we are trying to make it amorphous so that the all free ions can move easily from one side to another side, and which is fundamentally known as the charging and discharging of your material, or you can say the charging discharging of the capacitors or the rechargeable battery. The idea is by adding some plasticizers, or by adding some major salts, or by adding some graphite. Like in my research laboratory, my students are using activated carbon, graphite, and graphene to be added into the host polymer to make them convertible from crystalline to amorphous, so that ion can move easily when they are being sandwiched between two electrodes. So why are not safer? The question is why liquids are not safer. See, the main part is when we are coming with the electrolytes, and which has been due to of dispersion of different salt and all things, we are getting sufficient number of free ions which can move. But the problem is how they can move from one point to another point, and what are the factors which are impacting this movement, right? So the question is, ionic conductivity is measure of how easily ions can move from one side to another side. Then when I'm saying ions, it means how many charges are moving per unit time, per unit area. This is the charge carrier density, the concentration of mobile ions available for carrying the electric charges. Or this is the well-known formula you might be used when you are discussing about the conductivity, concentration, and mobility, where the sigma is my conductivity, n is the concentration of charge carriers. Maybe in my case, it's ion, and mu is the mobility of charge carriers when they are moving from one side to another side, right? So this is an example. Like if you have a very heavy traffic and your vehicle cannot move easily from one point to another side, but if you are providing a space, sufficient space for them, your vehicle can move fast and fast, and you'll get the good conductivity. If I'm taking these cars as an ion. So the unlocking the performance, we have different tools and different methodologies. We can add different salt, we can add some disperside, we can add some plasticizers, we can increase the temperature so that we can have the higher concentration charge carriers, or we can release and we can make free the ions to move from one side to another. So adding salt, increasing carrier density, but at the same time, it can reduce the mobility, because I can give an example. What is the relation between the concentration and mobility is? Suppose I have a corridor where few students are wandering, and see that if in that corridor only 2 and 3 students are there, they can move very easily from one side to another side. You can say that students have very high mobility. At the same time, the same dimension, same corridor, you have more than 100 students, and one want to move from one side to another side, then maybe the student face some problem because the concentration become very high and mobility may drop down. But sometimes we want higher concentration, sometimes we want higher N, and sometimes we want higher mu, higher mobility. It depends upon the material and depends upon the type of device what you are trying to fabricate, right? So this is very fundamental part of my study. And now coming down to the one very basic understanding that what is happening when we are increasing temperature. Because as I mentioned that if my material is highly crystalline and the conductivity will be low, although I have higher concentration of ions, but they have been trapped, they are not free to move. But if I increase the temperature, if the structure start melting, and if they provide the crystalline become slightly moving to the amorphous, then that trapped ions can move easily, right? So this is I'm saying that how concentration increases and how mobility looks when we have the temperature. So I will discuss this part in great detail. So impedance spectroscopy is a well-known method for characterization of ion dynamics or ion conductivity. Now, I'm coming down to more and more fundamental concept because I know that most of your students, the crowd is from undergraduate studies, I suppose. So there's a big difference because as I mentioned, it's a spectroscopy. It's an impedance spectroscopy. I'm not saying resistance, right? It's an impedance spectroscopy. So we have to understand what is the difference between the resistance and the impedance. Definition, if you go through, the resistance is the opposition to current to flow in a circuit measured in ohms and is a constant for both AC and DC current, right? But when you are coming with the impedance is the total opposition to current flow in an AC circuit, right? Which include both resistance and reactance and is the frequency dependent. So in general, if somebody asks you what is the difference between resistance and impedance, you can say that if you are characterizing your device just because of the AC circuits or just virtue of the frequency applied across the two terminals, whatever resistance is being offered, it will be counted as an impedance. And impedance always having the two component, which is the real and imaginary part. I'm leaving about the other parts. I suppose that you all must having the basic understanding about this what the resistance and impedance are, but still to make it complete, component only involve resistance. When in the case of impedance, it involves resistance and reactance both. Properties for ideal are values independent of frequencies because AC circuits are AC current is not applied, but when we are coming the impedance, it depends on the frequency. So AC current and the voltage signals are generally shifted in phase. And if you want to go into the formula, you find that both almost same because R equals to E by I and Z equals to E by I. But here the Z is showing that the characterization been done for the AC. So again, I'm not giving much time because I suppose I'm short of time, running short of time. So this is a simple formula that definition of the conductivity. This is the formula that R and J of I, where J stands for the imaginary part. So resistance and reactance, where the one is my imaginary part and another is my real part of the analysis. So what this idea is saying, let me is it visible? Yeah, okay, got it. So the circuit element that exhibit much more complex behavior, these elements focus on the abundant and simple concept of resistance. In the place we use impedance, which is more general circuit parameters like resistance. Impedance is a measure of the ability of circuits. This is all the theory part. You can read and understand this about. Let me move into the more important part. This is the frequency, how we are applying the omega is the frequency 2 pi f, and is also known as AC impedance spectroscopy or complex impedance spectroscopy as electrochemical impedance part. And no, what is happening is when we are applying AC signal to any circuit, And when it passes through the particular, you can say the thin film, which we have been prepared, and if that thin film is offering some different property like the reactants, then it might be possible that there is a phase shift between the signal of input and the signal of output. And when we are trying to find this phase shift, is a formula that is cos phi plus I of sin phi, where cos phi is my real part and I sin phi is my imaginary part. And this is the block diagram of the instrument of impedance spectroscopy. Now, when I got the data from the impedance spectroscopy, usually find the data in terms of real and imaginary part of impedance, Z prime and Z double prime. And when I try to plot a graph between these two parameters, that is the real part and the imaginary part of the impedance, you find a graph like this. Right? This is known as Cole-Cole plot. We usually draw two set of plot. One is Cole-Cole plot and the another is Bode plot. Right? Cole-Cole plot will give a very deeper information that how the transition phase going on and how the ions start moving from the one side to another side. And this is the higher frequency region, and at the lower frequency region, you get a state spikes. So I'm again leaving this part because the equivalent circuit and parameters will be a higher part for the students of undergraduate. So what actually happening is, coming down to this particular diagram, this is the ideal graph which has been obtained when we draw a Cole-Cole plot from the real and imaginary part of impedance spectroscopy or the real imaginary part of your impedance. But whenever you try to draw the graph out of the data which you obtain from the impedance data, you find some sort of distorted semicircles or this distorted graph. So what are the reason behind that? If you are getting the distorted semicircle, it maybe arises due to the overlapping of semicircle with various time constant. If it is depressed semicircle, maybe the electrolyte is not homogeneous or distributed microscopic property of the electrolyte. Slanted or the curved spikes may arise due to unevenness of the electrode-electrolyte interface, charge transfer across the electrode and electrolyte interface, diffusion of the space in the electrode or the electrode. This deviation is explained in terms of the new circuit parameters called as a constant phase parameter. You can see this diagram. At the higher frequency, you are getting this part, but at the lower frequency, you are getting this spike, right? So there's a two-way to find to get the value of RB. RB is the bulk resistance, which has been offered, which appear into get into the appearance, and you are sandwiching between the two conducting electrodes. There are two methods. One is to draw a circle where the circle is cut it out. Let me find some pen. This part is my RB value. Another method which will be used by many the researchers, that is the spike part. If you draw a straight line, if we extrapolate this part and the area where this cut it out, they take this value as an RB, right? So there are two different methods, but both the way. The first method is both accurate, that you can draw a semicircle, and the more important part is whenever you are trying to get the RB value out of the Cole-Cole plot, both the axes must be same. Both the axes must be same. If these two axes are uneven, then the semicircle, the circle part will not be drawn properly. In that case, suppose you are getting the data and it is not possible to draw data with the same homogeneous values on x and y. In that case, you can use this straight line spike value, and where the values extrapolated or cut out the x-axis, you can take that value. So there are two different methods. And you can see like this is not the exact graph which I shown earlier. If it is looks like this, that may be the perfect Cole-Cole plot, but it is not happening. So I already explained what are the possible reasons why you are not getting the proper the semicircle on your Cole-Cole plot, right? So Cole-Cole plot will give you a very inside information about your polarization across the electrodes, and it will give you the information how the ions are moving from one side to another side, and what amount of resistance is offered by that electrolyte which you have prepared in your laboratory. That is the RB value. So once you got the RB value, you can calculate the conductivity by using the I suppose I missed that formula. Okay. So the way of calculating the conductivity is sigma. Sigma is equals to 1 by RB. This RB value is which you have calculated this one, and multiply by the thickness upon the area. Thickness is the polymer electrolyte film which you have prepared, and area is the sample electrode which you have used to measure the impedance spectroscopy sample, right? So by this way, you can calculate the conductivity, and based on the conductivity, you can calculate the value of N and mu. This is another way of finding the value, or way of drawing the graph out of the impedance spectroscopy data, which you will obtain, and this is known as Bode plot, and this will give you the more insight about the frequency based or the angle based value, and this will also give you the idea about the hopping and dehopping of the ions, right? So aspects are frequency dependent behavior. This explain show how the system impedance magnitude and phase vary across frequency. Identifying the time constants, the peaks are or the inflection points corresponding to distinct relaxation process. It's known as RC element. This is distinguished between the capacitive, resistive region. High phase angle is the capacitive behavior, low phase angle is the resistive behavior, and negative phase angle is so the inductive behavior. So by the Bode plot, you can analyze that what sort of behavior is shown by your sample when they've been placed between two electrodes, right? And this is the Bode plot diagram, which have been taken from this reference to make you more understandable that the frequency and log of Z will give this sort of graph, and the frequency with the phase angle will give you this information, and this is the highest peak by which we can find the more insight on the phase one. This is the formula which I mentioned earlier, that this is the conductivity based system, and I'm coming down to three theoretical models which can be used to understand how this conductivity pattern goes up. Like you can see that when I enhance the concentration of CUI, the conductivity initially dropped down, and they dropped down to very extreme value, started from 10 to the power minus 4 and dropped down to 10 to the power minus 7. So what is the reason behind the drop in conductivity? Even you can understand what would be the reason behind the change in activity, maybe upper or maybe the lower side. So to understand that part, we have different equations. One is Vogel-Hammond-Poelcher equation or Arrhenius type equation. This is to understand the conductivity of your sample. These are some other parameters which we can study out of the data or the values obtained out of the impedance spectroscopy characterization. This is the dielectric constant, capacitance, epsilon prime, epsilon double prime. You can say the real imaginary part, modulus, AC conductivity, and the more interestingly, we can have the concentration and mobility based system. This is the Rice and Roth model. I will introduce the three different theoretical models which can be used to analyze how the concentration and mobility behaves. One is the Rice and Roth model, and Rice and Roth model is more best suited for the material which is the crystalline in nature, more crystalline, or maybe the partially amorphous. Another is Truchan model, and Truchan model is basically based on your diffusion constant value, D, which can be calculated from the 10 graph. And another is your SG model. I'm not giving more insight on the other two models, although I had included in my slide. But SG model is one of the most popular model, or the recent one, which people are using to find the value of N. So all these three models, you can see all these values can be taken out or can be analyzed directly from the impedance data. So you can again go through these three. This is the N again by the Truchan model. This is the Rice and Roth model. You can find the value of N out of this particular equation, because conductivity we already measured. All other data, unknown data, can be taken out from the impedance characterized value.
Doctor, we have 1 minute left.
Yeah, okay. I'm leaving it out. So this is the graph which we received in our recent publication we got in ACS Omega. You can see that all three models are having the different values. Different values are being offered. But interestingly, you can see that all these three values, the concentration of charge carriers are being increased directly just after the melting temperature, just after or just near to the melting temperature, because the structure is PEO based. So the PEO is offering the melting close to 60 to 70 degrees Celsius. You can see that at every near the melting temperature, the concentration of the charge carriers are being increases. In particular, when I am discussing about the Rice and Roth model or the SG model, you can say that the concentration has become constant, and this all because of the percolation or you can say threshold values of the N value. So all these three values, approach and limitation. Approach rising model is basically on thermally activated and hopping, and the limitation is only valid for completely crystalline and matrix. Tucan model is for dielectric material, SG is for complex amorphous material, and everybody has their own limitation. Which model we have to adopt is entirely based on the system on which you are working, right? So once you get the value of the concentration, you can calculate the value of mobility, and you can understand, you can see that how the mobility is going down. Once you have the higher concentration, just be focused on the SG, the black graph value. When the concentration increases, you can see that mobility of the same part goes decreases. As I already mentioned, that if you have a higher crowd, then there's typical deficiency to move the ions from one side to the other side. So this is the very well understandable that if you have higher end, then the mobility may drop down, right? So this is all about the my presentation. My idea of my presentation is to understand how the Trukan model, Rice and Roth model, SG model are being used, and how these models are beneficially for a student to understand how the conductivity patterns are going. And interestingly, nowadays you can use so many AI tools and machine learning programming or Python programming you can use to make your own model based on this equation, right? So this is all about my presentation, and I'm giving you one idea that how you can move forward, because for any energy storage devices, the main problem is the conductivity, how ions move. So when we have a coupled transport, they are always stuck out to move from one point to another point. So de-allocation is the one good point. So if somebody wants to work on the polymer electrolytes, if they want to use this electrolyte for the upcoming energy storage devices, then one can think about the idea that how we decouple the process so that ion can move very fast inside the electrode and electrolyte, and which can give you the good efficiency of rechargeable batteries or energy storage devices, right? So this is the future question for the all new coming researchers. They can think about this, and you're always welcome to understand how the impedance spectroscopy works and how the rechargeable batteries work, because my area is rechargeable batteries and solar cells. So we can have a collaboration in this area. Recently, we are moving toward the more nature-friendly energy storage devices. So we start working on biopolymer-based polymer electrolytes. We are avoiding to use any synthetic polymers which are environmental hazard. We are working on rechargeable batteries. We are using graphite and graphene to increase the conductivity. We are very effectively working on the ion irradiation effect on conductivity, because the city where I am residing is having the RR-CAT, and we have a good collaboration in that. So we can think about having some project on ion irradiation, and in collaboration with RR-CAT. We are working on supercapacitors, quantum dots, nanoparticles for natural resources, graphite, graphene-based polymer electrolytes, as I mentioned. These are my research scholars. Those are working on the area of green energy, on the working of biopolymers. Some of them are working on SCAP. SCAP is the simulator where we can simulate our solar cell efficiencies. We can make so many arrangements and parameters adjusted out that. So they all are working on this area. And this is all about my presentation. Now I welcome the questions. If somebody wants, can take my details or WhatsApp number. We can be in connect to have some future work. So I wish student get something out of that.
Meeting this conference and organizing committee. I would like to thankful. Today I will give some information about polymer composite for EMI shielding application. EMI is electromagnetic interference shielding application. I am from Fırat University. I'm Hülya Kaftelen Odabaşı. Our university is located in Elazığ city. I will give first of all some information about our city. This is Eastern Anatolia region of the Turkey, founded in around the former city of Harput. And there is also touristic and historical places in the Elazığ. Our campus is as Fırat University was established since 1967. It has 4 institutes and 16 faculties and 312 departments and many research centers. Here are some of the photos from Civil Aviation School, and we have some Phantom, Cessna and airplanes and Bell helicopter for training of the bachelor students. I would like to give some introduction about my presentation. First of all, I will give some information EMI sources, materials for shielding and application, conductive fillers for polymer composites, EMI shielding mechanisms and factors affecting the EMI efficiency, design principles and key challenges. Electromagnetic waves arising from the natural and artificial sources such as radio, television, telephone, Wi-Fi network, and base station, satellite communication radar systems. They negatively affect the human health as well as the electric and electronic devices. Electromagnetic waves cause the distortion of the signals in electric and electronic devices, damage or decrease their life and performances in the electronic systems. Therefore, electromagnetic shielding continues to attract in the fields ranging from the commercial electronics to aerospace systems and military electronic products. Let me show you some common application of the EMI shielding materials. They are commonly used in electronic devices, aerospace and military systems, and medical equipments. Metal-based materials such as steel, copper, aluminum are widely used to protect devices from EMI due to their high electrical conductivity. However, their high density, high cost, low corrosion resistance, low weight absorbing properties limit their use. Polymer composites offer several advantages compared to metal-based EMI materials, including the lightweight, low cost, more flexible, and better absorber wave properties. The conductivity of the polymer composites can be provided by the conductive fillers like carbon black, carbon nanotubes, graphene, graphite, and MXene. EMI shielding materials require not only conductive fillers but also the high magnetic properties and dielectric constants like magnetic materials. Polymer-based composites for electromagnetic shielding is often necessary to achieve highly conductive interconnected network with a low filler content. Here, some of the common EMI shielding metal materials, and as I mentioned before, although they have some advantages, their use can be limited due to their disadvantages. And according to the electromagnetic shielding mechanisms, if the shielding materials needs to obtain better electromagnetic performance, it must have good conductivity. Electromagnetic shielding mechanisms here represented the ability of the material to attenuate the incident EM radiation. There are three mechanisms that contribute to EMI shielding, namely reflection, absorption, and the multiple reflection. The total EMI shielding efficiency is sum of these three mechanisms, and the reflection power is related to the interaction between the conductive parts of the material and the impinging the electromagnetic field, while the absorption is related to the absorption of the EMI waves by materials with high dielectric constant and high magnetic permeability. Here you can see a vector network analyzer that operates according to the coaxial transmission line method for EMI shielding measurements. In this method, it is possible to resolve separately the shielding effectiveness due to the absorption, transmission, and reflection. And in addition, the coaxial transmission line method, open field, and shield box methods also used to evaluate EMI shielding effectiveness. Vector network analyzer detects the complex scattering parameters we call the S parameters. Based on these parameters, information about the permittivity, permeability, as well as the EMI shielding efficiency can be obtained using the suitable algorithms or models or iteratives. Many factors affecting the EMI shielding performances of the polymer materials. These are mainly the filler type, size, shape, and aspect ratio, and properties of the constitutions and permeability, permittivity, electric conductivity, and properties of the matrix and filler materials, and the structure of the composite, bulk composite, multi-layered, and sandwich structure, foam structure, and the manufacturing methods, melt mixing, compression, and injection molding, and additive manufacturing, solution mixing. This diagram illustrates the principal categories of the conductive network architectures employed in electromagnetic interference shielding materials. Each segment represents a distinct structural strategy, such as multi-layer, multi-phase, foam, aerogel, biological and 3D printing, and segregated structures. They highlighting how different microstructural configuration facilitate the formation and continuous or interconnected conductive pathways. These conductive networks play a critical role and in enhancing the EMI shielding effectiveness by promoting the mechanisms such as reflection, absorption, and multiple scattering of the electromagnetic waves. And low reflective design is important design parameter for polymer composites. Pores improve the impedance matching at the air shield interfaces by affecting the surface conductivity of the shields, and also they create more internal impedance mismatch interfaces to increase the attenuation of the electromagnetic waves through the multiple reflection and scattering. Here are some of the examples presented about the factors affecting the EMI shielding. Here you can see as an example one of the work showing the size effect of the carbon fiber fillers. These carbon fillers containing the magnetic materials. As the carbon fiber length increases within the polymer matrix, more effective and continuous pathways are formed, and this enhances charge transport and electromagnetic wave attenuation. Also, the porous structures can be seen here. This contribute to multiple reflection, resulting in higher overall EMI shielding performance. And effect of polymer composite structure can be seen here, and the solid and foamed structure polymer composites. EMI performance of the electric conductivity volutes and foamed and solid polymer composites are compared here, and compared to solid polymers, foamed polymers exhibits good electrical conductivity with a lower filler content. It was demonstrated that the foaming would make the carbon nanofiller redistribute and oriented around the cells, resulting in more efficient interconnected conductive pathways throughout the composites. Other than the absorption and reflection, there is also multiple reflection was another important shielding mechanism. Existing of the carbon nanotubes and the formation of many cells could provide a large quantity of the interfacial area. Effect of nanofiller geometry is given in this slide. The size effect of nanofiller metals in polymer composites with the effects of carbon nanotubes and graphene plus carbon nanotubes on the polymer matrix materials. Carbon nanotube-based composites shows the superior electrical properties compared to graphene-based composites due to the rod-like geometry of the carbon nanotubes. This facilitates the dispersion of the carbon nanotubes particles and the formation of the carbon nanotube conductivity network within the polymer matrix. The rod-like geometry and the smaller surface area of carbon nanotubes compared to graphene decreased the reflection of the radiation at the composite external surfaces. In addition, the conductive carbon nanotube network within the polymer matrix has facilitated the absorption of the EMI radiation. Another affected factors is the fabrication methods. The fabrication methods plays a critical role in determining the dispersion, alignment, network formation, and conductive fillers within the polymer composites, and this directly influencing the EMI shielding efficiency. Techniques such as melt blending, solution mixing, and the in-situ polymerization each offer different levels of the structural control, and this ultimately affect the balance between the electrical conductivity, mechanical properties, and large-scale manufacturability. This table compares the different fabrication methods used for the polymer-based EMI shielding materials and highlights how the processing control the final performance of the materials. Methods such as in-situ polymerization and layer-by-layer assembly provide superior dispersion and the filler alignment, resulting in higher shielding effectiveness. In contrast, scalable techniques like a melt blending offers easier manufacturing but generally yield moderate EMI shielding performance due to their limited nanoscale control. This table shows that the balance between the process complexity, filler distribution, and structural precision determines the shielding quality of the polymer composites. Here is some example about the effect of processing technique and immiscibility of the polymers on EMI shielding performance. This figure shows that the total EMI shielding of the samples prepared by different processing strategy as a function of the frequency in X-band region, different preparation approach and blend composition alter the level of the selective localization, nanodispersion, and the phase morphology. Consequently, EMI shielding efficiency of the blend nanocomposites is varied, and the solution technique is better EMI attenuation and colorate, better dispersion of the filler. And here also we can see the single polymer with filled with the multiple carbon nanotubes, and the immiscible polymer blends with the fillers. Multiple scattering affect the polymer blends nanocomposites, make them more effective than the single one. And optimization strategies for the, if you look at the optimization strategies for the EMI shielding performance, EMI shielding performance of the polymer composite is strongly controlled by how well the conductive fillers are dispersed, how effectively they bond with the polymer matrix, and the microstructure that forms during the processing. Achieving the high shielding levels, typically above the 40 and 60 decibel, requires the carefully optimized fabrication techniques and filler design strategies. Future research is moving toward the hybrid filler systems, 3D engineered conductive networks, and the environmentally sustainable conductive polymers. And lastly, as you know, the polymers are naturally insulating materials. So achieving effective EMI shielding requires creating continuous conductive networks using the fillers such as graphene, carbon fibers, or metal particles. One major challenge is obtaining a uniform dispersion of these fillers, because agglomeration disturbs the conductive pathways needed for EM attenuation. Although increasing the filler loading can enhance the shielding effectiveness, it often leads to reduced mechanical flexibility and poorer processability. In addition, polymer composites may suffer from limited long-term stability, such as heat, humidity, or oxidation. They degrade their electrical performance and also affect EMI shielding performances. Finally developing the fabrication methods that are both scalable, cost-effective methods remains a significant challenge for widespread industrial adoption. Thank you for listening, and here is some of the MSc and bachelor students working in my lab, and also my collaborators. Here is my contact details. You can contact me. Do not hesitate to contact me. Thank you for giving this opportunity again. I am also open collaboration. Thank you, Felipe.
Thank you very much, Professor Kaftelen. We have time for one question.